Well, good afternoon, everybody. I'm really excited to be in Japan and talking to you all. My name is Nikitas Stamatopoulos. People call me Nick for obvious reasons. And today I will talk to you about quantum computing at Goldman Sachs, present some results, some recent results that we've done in the space, and try to give you an idea about how we view the quantum computing space at a firm like Goldman Sachs. So our mission is what exactly? Our mission, the way that we describe it to our peers and the people in the bank, is that we try to find quantum advantage and build quantum advantage for the firm and its clients. So the work is done in a small group of 7 people that we call R&D Quantum. It's part of the engineering division, and we interface a lot with the business side of the bank to understand the problems or the bottlenecks in terms of computational cost and areas where big speed-ups could translate to significant advantage for the business. And the way we define quantum advantage is obviously a solution to valuable problems that we have at the firm today, or we envision we might have in the future, and try to tackle them with a quantum technology that is better than any classical alternative in some way, whether that means we can compute something faster or cheaper or provide a better solution to a problem than what we can classically. And as I mentioned, we work very closely with the business. We have 3 key areas that we do research in at the moment in terms of quantum computing. And broadly, this is risk, managing risk, computing risk, and in general simulation, optimization, and machine learning. I think you might have heard people talking about these areas in other talks. It's quite a big part of our business and where the computational cost enters. So they seem an obvious choice to look at for quantum advantage. We are committed to publish research that we do. Our view is that by publishing our research, not only it accelerates the development of quantum algorithms, but in doing so, in presenting a quantum roadmap for applications, we're hoping to leverage the industry towards areas that will be beneficial for us. So we're looking at a situation of symbiosis, essentially, where we provide and try to direct the industry towards what we find interesting. So I'll briefly go over this. I'm sure everybody has some idea about why we're interested in quantum computers. But the main idea, and this is a little bit of qualitative statement, but we'll go into a little bit more detail a little later. Quantum computing power scales exponentially with qubits. Right, so that's kind of a rule of thumb that you can think about. You can take with a grain of salt, but the idea is that n classical bits can be used to simulate log n qubits. So in practice, what does that mean? So if we think about the Commodore 64, which was a computer that was introduced in the 1980s, you can use a Commodore 64 to simulate a quantum system comprising of 10 qubits. Now, if you increase your quantum system to 30 qubits, then you probably need some instance in the cloud, perhaps. So an AWS M4 instance could potentially simulate a system with 30 qubits. And if you then go to 60 qubits, you probably need the entire global cloud to simulate the behavior of the quantum system. And you might notice that these numbers, 30 and 60 qubits, are approximately the size of today's systems that are publicly available by a lot of hardware companies. But there's a very big caveat here in that today's qubits are imperfect. Right? And we'll see how that translates into difference in looking for quantum advantage. So I said that I will go into a little bit more detail about where the exponential power comes from. Right? So you can think of a quantum computer as a system where you have n qubits of input, and every clock cycle, at every time step, you can think of it, every operation or layer of operations you do, it produces an exponentially large matrix, complex matrix multiplication. Right? So every layer of operations you do an exponentially large matrix multiplication. And again, there's some caveats here that because there's noise inherent in the system, there's a limited number of multiplications you can do. So it limits how many time steps or clock cycles you can operate on a quantum computer before the result becomes too destroyed by the noise. The matrix multiplication is not, you cannot do arbitrary matrices. You have to, first of all, be able to represent them in a quantum system, and you need to be able to create them efficiently on a quantum computer. And there's another key point that I think is quite important, and I would like to pass this message through. I find it quite intuitive, is that even though you have this exponentially large matrix multiplication, your input and your output are quite limited. Right? So if you start with n qubits, your input will be a polynomial function maybe of the n bits, and after you perform the series of matrix multiplications over every step, your output will still be something of the order of n bits. Yeah. So there's this big memory, small pipe mental model that I like to think of quantum computing. I think it makes sense, and if you're thinking about a problem and thinking whether quantum computing could be useful for that problem, if it fits this model, it's probably worthwhile looking more into it. And perhaps the most famous example of a quantum computing algorithm which provides an advantage, Shor's algorithm for factorization, you can see how it fits this mental model, right? Because your input is a number you want to perform prime factorization in. You need to do a lot of steps, but in the end, you're interested in a prime factor. Right? So I like to think of this mental model as the appropriate types of problems that are amenable, let's say, to quantum computing. So this big memory, small pipe mental model, hopefully it makes sense to everybody. Okay, so how do we look at quantum research at Goldman Sachs? We've taken the approach of doing our research in a backwards way. So we start from a problem that we know is interesting from a practical point of view to our business, and we try to work out the resources that are required for that problem to be beneficial if you run it on a quantum computer, as opposed to starting from something small and then try to build it up to where you need to be. And sometimes if you start small and try to make statements about how generalizable your conclusions are, you often find that you might have missed some important details. So we like to work backwards. We know what we're interested in today, so let's work backwards and try to figure out what quantum resources are needed for that problem to be useful to run on a quantum computer. There is one, I think, quite important aspect which makes quantum computing research quite interesting from financial applications, is that we usually can ascribe a number, a financial indicator of what a speed up would imply for our business. Right? So if we say that using this quantum computer will give us a 10x advantage, it's kind of easily translated to a dollar value, so to speak. And I think that adds a little bit of help in trying to motivate research in quantum computing. However, the financial applications, they're not obviously quantum native. So if you're thinking about material science and design or quantum chemistry, then in a lot of cases there's a very easy correlation or mapping between what you want to do and how you would do it on a quantum computer. For financial applications, usually you have to think a little bit differently about your problem than how you think of it classically. Okay, I think this is a translation. Okay, so we have essentially 3 steps that we think about the research of quantum computing at Goldman Sachs. The first is the resource estimation I just described. So work backwards from the end result and figure out the components that make up that are required for the implementation of your problem on a quantum computer. And then once you have this roadmap, then try to find individual parts that you can enhance, either by coming up with a better algorithm for the subcomponent, or better gate synthesis. There's a lot of things that you can do. And then eventually, we're also thinking about hardware integration. So we're talking to a lot of hardware companies in the field, try to understand particularly, or especially, what does error correction imply for these applications. And error correction, I'm not sure how many of you have thought about error correction and fault tolerance in general in quantum computing, but for some application, it seems that it will be quite imperative to have a very good error correction code and implementation and everything that comes with it in order to be able to squeeze out some benefit in these applications. Yeah, so our collaborators include people from industry and startups and various academics. We're quite open to the ecosystem, and our publication is trying to work together with our collaborators. So I will now discuss a little bit where we are today. And through these, the next few slides, I'll try to place quantum advantage in finance in the broader context. So this graph, hopefully, will give you some idea of how we think about these problems. We call this a landscape of quantum power. On the x-axis, you have the number of qubits that might be available to you on a quantum computer. And on the y-axis, you have a measure of the program depth that you're able to run. So, how big of an instruction set can you get away with running for a particular number of qubits? And these lines, they're there to indicate that for a particular error rate on your quantum device, it limits you a little bit of where exactly you can be in this graph. You cannot be in any arbitrary point for a particular noise characterization. Perhaps you can do few things with a lot of qubits, or you can do a lot of things with few qubits. So there's a trade-off that you have to decide, which is inherently described by the error inherently present in the quantum systems. And we can make, and this is somewhat qualitative picture, but I think it might be helpful. We can put a line around the 50 qubit mark and say that this is the HPC horizon. So above that, or to the right of this graph, it's going to be really hard to simulate the computation of a quantum computer, or the execution of a quantum computer. And there's two areas that we can put perhaps on the right of this map, because we do have access to some of these 50 qubit machines, even though they're quite limited in terms of the number of things you can do with them because of the error. So there's the NISQ era, which maybe is somewhere there, but it's to the right of this graph as far as we can tell, or as far as we estimate. And then on the top right, you have the more standard algorithms like RSA factorization and Grover's algorithm, algorithms for which we have theoretical understanding that they will perform better than classical computers. In the NISQ era, we don't really have some guarantees like that, but it's something that people are interested in. So the QPUs today, we can think of them as to the lower left corner, which is not where we want to be. We want to be in the top right corner. But it's a process, and we've put a few dots there that maybe you have heard about. Obviously, the quantum supremacy paper from Google would put the device at that point, and some more supremacy announcements were made. So maybe I should update this to include a few more points. And there's the quantum hardware obviously is progressing. So the IBM chip of 127 qubits, I think, would lie somewhere there. But what we want to do is make sure that given what we have, the access to the QPUs that we have applications that will eventually meet somewhere, right? And to that point, I would like to show you. So one of the pieces of work that we did with IBM towards the end of 2020 was to take, in the manner that I described of working backwards, take a derivative pricing problem for which we have a theoretical understanding that quantum computers have, at least from a complexity point of view, an advantage over classical computers. We did the resource estimation, and we found for a particular type of derivative that is of practical value to our business, we would need about 8,000 qubits and a program depth, which we measure in terms of T depth, around 50 million. So we can place that over at that point. And so as we see the progress of quantum computing, there's two things that we need to do. One of them is push to the top right, those red dots, and then push to the lower left corner, the green dots. And while we talk to the hardware providers about the quality of QPUs today, we try to do our part to bring the green down. And obviously, this is we don't really have access to hardware that can run that at the moment. So our estimates, we might be overestimating. Hopefully, we're overestimating. But as we get access to bigger and better hardware, we can get more concrete in that. But we try to do our part. So in follow-up work, we extended the derivative pricing problem to do a little bit more than just calculating the derivative price. And in this case, this is we try to calculate the Greeks or sensitivities of the derivative price of the input parameters, which is also useful to us as a business. And we did some optimization, so there is a little bit of an enhancement there. But there's one more key point here that I would like to pass through, is that so when you think about quantum computing applications for which classical computing faces an impossible task, so you might have heard that in order to do something classically, you need 100,000 years, right? Now, if that's the case, you don't really care that much, I mean, assuming you have a quantum advantage, about how fast your quantum computer is. But in problems like derivative pricing, where we do them today, we do have ways to do them today, and we can ascribe an amount of time that it takes us to perform this calculation. We have to make sure that the quantum computer will be fast enough in terms of wall clock time in order to match the classical speed. And so for the original estimation of quantum advantage for the derivative pricing problem, we had estimated that we require 50 megahertz, and this is quite a lot of very high speed of execution for a quantum computer. So our follow-up work, we reduced that by a factor of 7 approximately, which is still quite high, but we still think that there might be some more we can gain from there. So we try to fill in this map essentially as much as we can. And again, an important caveat here: the x-axis is number of logical qubits, right? This is a number of perfect, essentially, qubits that you have access to. So this is quite an important point. Okay, so let me move on. One of the other results I wanted to briefly mention is this concept of low depth amplitude estimation. Amplitude estimation is the algorithm that we use for the derivative pricing problem, and we asked ourselves whether there is an intermediate area where we can, because we have such big circuits that we calculated, as you saw in the previous slide, for quantum advantage. Well, can we make them shorter and give up some of the speed up? Is that possible? And just to give you a little bit of a context, right? So the amplitude estimation is essentially calculation of an expectation value, which classically, if you want to do it to an accuracy epsilon, would require 1 over epsilon, or scale as 1 over epsilon squared. So just as a principle, if you have a 10 to the minus 3 target epsilon, then you need 1 million samples. Again, this is a big O notation, so the constant factors, they depend really on your problem. But quantum amplitude estimation reduces this to 1 over epsilon samples. So in the same manner as the classical counterpart, if you want an error of 10 to the minus 3 in your estimation, you would require now 1,000 samples. Right? And this is where why we expect there to be an advantage in derivative pricing, at least from a complexity point of view. And so can we have any trade-off between these two regimes, where one of them is fully classical and goes 1 over epsilon squared, and quantum goes as 1 over epsilon? It turns out that the answer is yes, and our team developed a couple of algorithms which the trade-off, the 1 over epsilon, if you can see. So you have factor beta. There's this beta that you can tune in and see what works best for your application. Now, this is a quadratic speedup, so you're probably going to need all the speedup you can get. But our estimation or our hope is that having access to this trade-off will allow us to better estimate the resources once the devices become, well, better, let's say, larger and more efficient. So we find this possibly quite useful result. And in collaboration with IonQ, we also run some of these on actual hardware. There is a couple of references on the papers here. I don't have too much time to go into detail. I wanted to just briefly mention a recent result that we published in Archive about a month ago. The topic is block encoding a matrix of classical data. That's a little bit of an esoteric problem, perhaps. But just quickly, the block encoding of a matrix, A, which you can think of, it could be a complex matrix, is a unitary, so that the top left block of the unitary U is a scaled version of your matrix A. Yeah, so you can think of A as a matrix of classical data that take part in your classical calculation. Obviously, the quantum computing unitary, the quantum computer can only really do unitary transformation, so you need to transform it perhaps to make it possible to load it on a quantum computer. And the notion of block encoding is particularly lately used in a lot of applications. So used in conjunction with the quantum, well, the QSVT, the quantum singular value transformation framework, it can perform almost arbitrary polynomial transformations on the singular values or the eigenvalues of a particular matrix. And this comes in handy for some applications like linear systems, Hamiltonian simulations, some areas of quantum machine learning. And there's a lot of interest in this field. So we thought, OK, let's figure out what does it really take to do this block encoding. Sometimes it's used as an input model. Algorithms say, OK, assume you have access to block encoding of your matrix, then here's what you do. So we try to tackle the resources for that. And I would really point you to the paper if you want to go into more detail. But one thing I wanted to point out here is a couple of numbers from this table. So first of all, we have made some advancements, some enhancements in the way of doing this block encoding given to what was there before. And we do have essentially a way to trade off a depth for the number of qubits. All right, so if you think about block encoding a matrix of 4,000 by 4,000, for a particular accuracy epsilon, which we don't need to go into too much detail here, you can see, so you would require 70 million qubits and a t-depth of 800. It was, a t-depth of 800 is not that bad. If you remember from the derivative pricing problem, we need 50 million, right? But you can also think of it in a different context, where instead of having 70 million qubits and 800 t-depth, you can get the same performance for about 20,000 each. Right? But again, you need 20,000 qubits to encode a matrix of 4,000 by 4,000. And applications of block encoding, whether that's machine learning or linear systems, they can easily go to 10,000 by 10,000. They can be almost arbitrarily large. So what we try to do here is make the resource estimation. We've made some enhancements that I mentioned. But one thing you should take away from this is going back to the mental model. If you have all this input data, then it's going to be really hard to squeeze out advantage out of a quantum computer. And yes, I'm a little bit over time, but this is the last slide. So as I mentioned, we work backwards for a quantum advantage. We're always looking for potential collaborators, and I would highlight 3 areas that we're looking to collaborate with people on. So we're looking at improvements to relevant algorithms or ideas about new algorithms. Obviously, that's always welcome, especially super quadratic ones, because quadratic speedups are they're going to be really challenging proposition in terms of error correction. And we're always interested in ways to approach quantum error correction, whether that's a particular architecture or some particular code. But we're very interested in this area as well. And since we're doing a lot of risk estimation and it's a very painstaking process to do, we're always interested in tools that help us in this manner. Please feel free to email me with any questions or any ideas about these improvements. Thank you very much.